Welcome to qnawire.
In this problem, we're looking at a regeneration power plant with an added process heater that is taking steam from the turbine. Our water is starting coming out of the condenser, going into the pump where it's being pumped up to 0.4 megapascals. It enters the open feedwater heater where it mixes with some of the steam from the turbine, and then exits as a saturated liquid, going into the second pump where it's pumped up to its 6 megapascals. It enters the boiler where it comes out at 450 degrees Celsius, and then enters the turbine where it exits in two stages. First, going to stage 6 and 7 to the process heater and the open feedwater heater, respectively, and then at 0.4 megapascals, and then at stage 8 at 10 kilopascals, where it goes into the condenser, where it is cooled by water from a river flowing at 463 kilograms per second. We're told that 60% of the steam is extracted at part Y at stages 6 and 7, and we know that the specific heat of water is 4.22 kilojoules per kilogram per degree Kelvin. Okay, what we're looking for here is the power output of the turbine, the temperature change in the water going through the condenser, the rate of mass flow through the process heater, the heat being supplied to the process heater, and then the heat being supplied in the boiler. So with any question like this, we're going to start out just finding the enthalpies at every point in the system. I already have a few just from the various pressures and temperatures given throughout the problem. So past that, we're just going to have to calculate the rest. So first, H2. We're having H1 go through a pump, so we're going to use the work done by a pump formula, which is equal to the specific density times P2 minus P1. And of course, because of the conservation of energy, H2 is going to be equal to H1 plus the work done on it, which, as I just said, is the specific density times P2 minus P1. So we have all of these things. H1, V1, P2 is 0.4 megapascals, P1 is 10 kilopascals, so we can calculate H2, which is equal to 192.20. Whoops. H3 to H4 is going to be the same process. We're going through a pump. The only difference is our subscripts are going to change. So this will instead be H4 is equal to H3 times V3, P4 minus P3. Same thing here. We have all these numbers. P4 is the 6 megapascals. P3 is the 0.4 megapascals. So we can get our H4, which is 610.73. Okay. For 6 and 7, they're going to have the same enthalpy. And 8, we're going to use the steam quality equation. We might just look at the tables in the back, but we will find that it is below the saturation point of the steam. So we're going to just calculate it based on the steam quality. So our steam quality equation is H6 we'll start with is equal to HF plus the steam quality times HFG. The steam quality is equal to the entropy, so S6 minus SF over SFG. And because this is an isentropic turbine, the S6, the entropy out will be the same as the entropy in, so this will be equal to S5. So we can plug that in up here. S5 minus SF over SFG times HFG. Okay, so now all we need to do is plug in our S5 that we got from the superheated steam tables and plug in our various entropies and enthalpies of saturated liquid and vaporization. At this point, here's 0.6, I have 0.8 down here. So start with 0.6 and we'll just calculate it out, and it will be 2665.7. And as I said, that'll be the same as 7. The only difference between 6 and 7 is the amount of steam going to each one. For H8, as I said, we're going to be doing the same thing. The only difference is we'll be using our lower table here for the vaporization and saturated liquid enthalpies and entropies. And that will get us 2128.8. Okay, and with that, we're ready to start solving for our the values that were asked for in this problem. Starting with the power output, in order to do this, oh no, we have everything we need for this. So, because we have our Y here, the power output is just going to be the work times the mass flow rate. We have the mass flow rate, so now we just need the work, and we have a formula for that. In this case, it will be H5 minus H6 or 7, doesn't really matter, I'll just say H6, plus, okay, so that's the work for all the steam, which is going from 5 to 6, and then the steam that isn't extracted there continues losing energy going from 6 to 8. So that will be 1 minus Y times H6 minus H8. So if we solve for this, what we're looking for here is the power output. So all we need to do is multiply this by our mass flow rate. And we'll get the power output. So just plug in our numbers here. As I said before, our Y here is 0.6. And we can get the power output, which is 17 megawatts. Okay, next, the temperature change in the water going through the cooling water going through the condenser. To do that, we'll be looking at our conservation of energy, our Q in, that's equal to our Q out. Our Q in is coming from the energy loss between stage 8 and stage 1. And our Q out is coming from, we're going to the water in the river. So our Q in here is just going to be the mass flow rate of the steam times H8 minus H1. And our Q out will be the mass flow rate of the water times the energy going into it, which, since we want our change in temperature here, we will use the formula to convert between the temperature and energy, which is the specific energy times the change in temperature. Now all we need to do is solve for our delta T, and all we need to do is divide by the mass flow rate of the water and the specific energy. So this would be ms H8 minus H1 over mw Cp. But we have to remember here that the mass flow rate of the steam here isn't the full picture, because 60% of the steam has been extracted back here. So actually what we're looking at here is 1 minus y times our ms for the top. And of course our y here is 0.6, so our 1 minus y will just be 0.4. So anyway, we can just plug in those numbers and get our temperature differential out of it, which will be 7.93 degrees, or for this problem, rounding to 1 sig fig, 8 degrees Celsius. Okay, next the mass flow rate through the process heater. We can calculate this by calculating how much water needs or steam needs to go to the open feedwater heater in order to heat the water enough that it comes out saturated, because that's what the open feedwater heater does. So once again, we're going to be looking at our conservation of energy. Our Q in has to be equal to our Q out. Our Q out here is just going to be the energy leaving at 3, which is going to be H3. But we aren't counting our percentage of the steam that's going to the process heater here. So this will actually be 1 minus Z times H3. So then that will be equal to our Q in. Our Q in is coming from 2 places. First at 7, which is only a fraction of our Y value. So it will be Y minus Z times H7, plus the energy coming in at 2, which is 1 minus Y times H2. So now all we need to do here is solve for Z, and then we can multiply that by our total mass flow rate of the steam to get the percentage, or the mass flow rate through the process heater. So what we have here, H3 minus Z H3 equals Y H7 minus Z H7 plus H2 minus Y H2. Okay, now we can separate these by their letters. We obviously want to isolate Z, so I'll move this ZH7 over here, move the H3 over there. We'll get ZH7. I'll just factor out the Z right away. Minus H3 is equal to, and I'll factor out this Y too. Y H7 minus H2. And the rest of this is plus H2 minus H3. Okay, and now just divide through by this term. Z is equal to Y H7 minus H2 plus H2 minus H3 over H7 minus H3. So this will get us the percentage of steam flowing through the process heater. Then all we need to do is multiply by the rate of steam flow, and we will get our rate of mass flow through the process heater, which will be 10.4 kilograms per second. Okay, now for the heat supplied per unit mass of the process heater. This is an easy one. All it is the heat that is lost in the steam going through the process heater. So that's just our H6 minus H3. Which is equal to 2061 kilojoules per kilogram. Okay, and then finally the heat input of the boiler. This one we have a formula for. Our Qn is just equal to our mass flow rate times the energy input, which I just said is just going to be the difference in the enthalpies at those states, so H5 minus H4. We have our mass flow rate, we have our H5, we have our H4, so our Qn is going to be 53843, or rounding up for this problem, 53.8 megawatts.